Okay, thank you, Professor Riddhi, for this invitation to deliver this talk in this Gyan course. So I will speak on this a brief introduction to Finsler geometry. So it is somehow it is related with your this Gyan course given by Professor Athenes Papadopoulos, and it is in fact some of the results also I will include it here in these slides are of it's done by Professor Athenes with his collaborators. So let me, introduce about a little bit about the historical development of this Finsler geometry. So in fact, it was started long back uh, by Riemann in his famous lecture of 1854 entitled "On the Hypotheses Which Lie at the Foundation of Geometry," where he discussed about a metric which is more general than square root of a quadratic differential form. In particular, a metric which is fourth root of a quadratic differential form. The origin of Finsler geometry seems to appear in this habilitation lecture. Formally, it was introduced by Finsler in 1918 in his thesis under supervision of Carathodori and developed by several geometers like Taylor, Burward, Cartan, Bushman, Run, Hashiguchi, Matsumoto, and towards the end of the previous century by S.S. Chern. And still, it's going on. So, as everybody knows, this Riemannian metric on a smooth manifold is a smoothly varying family of inner product on the manifold. So, those who do not aware about manifold, you just assume, suppose I'm considering U as an open set, and the whole procedure we can develop on some open set of Rn. Now, if you take any curve on even open set of Rn, maybe the arc length of a curve you can determine by integrating its speed. So it actually requires a norm on each tangent space of the point of the curve. Now, a reasonable tool to compute the arc length of curves is a Riemannian metric on the smooth manifold, which is everybody know that is smoothly varying family of inner product on the manifold. Now, one can ask a question that can we talk about family of norms rather than inner products on the manifold? And the answer is yes. Such a norm is Minkowski norm, which I will introduce soon. And a Finsler structure on a manifold is actually a family of Minkowski norm, one on each tangent space of the manifold. So here is a definition of Minkowski norm on a vector space first. So let V be an n-dimensional real vector space. So a continuous function f from V to R is called a Minkowski norm if it satisfies the following conditions. So the first condition is that what is called non-negativity condition. So this norm is, it's usual norm of functional analysis, everybody knows. The only difference from the functional analysis norm here that in functional analysis you take this norm of k chi is equal to modulus of k norm of chi for any real number k, and here I am taking only this positive homogeneity, that is norm of k times xi is equal to k times norm of xi only for positive numbers. What it means that norm of minus xi may not be equal to norm of xi here. So this norm is not symmetric in some sense, right? And this triangle inequality. So if I am considering such a norm, what is called a Minkowski norm. So in fact, there is also a notion of weak Minkowski norm. So there, here is, there are vectors, so which are non-zero vectors but having norm 0, right? So such a norm is called weak Minkowski norm. But for the moment here, I am only considering this Minkowski norm. And some stronger notion of norm I will consider. I mean, because we are working in differential geometry, so I wanted to introduce differentiability at various level. So I introduce a stronger version of this Minkowski norm. So a Minkowski norm on V is said to be strongly convex if it is smooth on V minus, I mean, non-zero part of the vector space, and the Hessian of F square at any point, at any non-zero point, is positive definite, right? So this is called a strong convexity condition. In fact, if you consider a function f from V to R, which is smooth in non-zero part of the vector space, satisfying this second condition, and this is strong convexity condition, it actually implies this first condition and third condition. So you can think of a strongly convex Minkowski norm as a function from f from V to R satisfying this positive homogeneity condition and strong convexity condition. So the consequence of this strongly convex Minkowski norm is that for any non-zero vector, it must be positive, right? And the second, this triangle inequality comes, I mean, as a consequence of this strong convexity condition. So, I mean, in some books, this is strong convex Minkowski norm is said as Minkowski norm itself. And in fact, Finsler structure is I mean, in some sense, a smoothly varying family of this strongly convex Minkowski norm, which I will soon uh, define. Now, here is a notion of indicatrix. It's actually a kind of unit sphere for the given norm. In Finsler geometry, it's well known by indicatrix. So, the unit sphere centered at origin is called indicatrix. It's very important for our purpose. And the geometrically, this is strong convexity means that this indicatrix is actually a hypersurface of strictly positive Gaussian curvature, right? So this strong convexity, this implies that the as a hypersurface, this is indicatrix has strictly positive Gaussian curvature. Now, so for this strongly convex Minkowski norm, among LP spaces, only this is strongly convex Minkowski norm if and only if this P is equal to 2. That is only Euclidean norm among all the LP spaces or strongly convex Minkowski norm. Although you see this, if you just consider only Minkowski norm in this previous definition without this strong convexity condition, for all P it's actually Minkowski norm. But for strong convexity, only this Euclidean norm satisfy this condition. In fact, for P lies between 1 to 2, this smoothness condition is violating, while when you take any P greater than 2, this strong convexity condition is violated. Now, the next definition, next example of a Minkowski norm, if you take a Euclidean norm on R2, right, this y1 square plus y2 square, if you take any vector y in R2 with coordinates y1 and y2, and you take any real number b, positive real number b, which is less than 1, then if you define a function f from R2 to R like this, it's actually satisfy all the condition of a strongly convex Minkowski norm, and therefore it is strongly convex Minkowski norm, right? You can prove that it's, the square, the Hessian of the square of this norm is actually positive definite. Now, how it differs with this Euclidean metric? I mean, there are some, these are propositions, these are very important propositions. So, in most of our discussion, I will only talk about the results. Rarely I will prove anything, but just because I'm giving some overview about this Finsler geometry, so I will say mostly about the results rather than going in the proof. So, how this Minkowski geometry is differ with this Euclidean geometry? So let Rnf be a Minkowski space. So here I am considering just Minkowski metric, not strongly convex Minkowski metric, and delta be this Minkowski metric induced from F. That is delta, and the distance between 2 point x and y is defined by this Fx minus y on Rn. then this delta is Euclidean if and only if the ball centered at any point A and any radius r is an ellipsoid. So in fact, it's a necessary and sufficient condition for this distance induced by this Minkowski metric is Euclidean, is that this ball centered at any point, in fact you can take your point as origin, and any radius is an ellipsoid. And here is second important proposition. So if delta B is a Minkowski metric on Rn, then every isometry of delta is an affine transformation of Rn. And the group of isometries of delta is actually conjugate to subgroup of the group of isometries of Euclidean space, right? Further, this isometry is conjugate to the full group En. So here it's conjugate to subgroup of group of isometries of Euclidean space, and your delta becomes Euclidean if and only if it is conjugate to the full group of Euclidean isometry. This is the distinction between how you can differentiate this Minkowski metric with Euclidean metric. Now, this result is for strongly convex Minkowski space. This result is very much useful for further investigation. So, if Rn with F be a strongly convex Minkowski space, then this square of the norm is always C infinity away from the origin. But at the origin, it is just C1 and it has all derivatives as 0. But the third condition is very important, that it is C2 at origin if and only if F is Euclidean. So this is again, a kind of differentiation between this Minkowski space and Euclidean space. So if this square of the norm is C2 at origin, then this F is Euclidean, and other way it's trivial. Now, a Finsler metric on a smooth manifold is a continuous function f from tangent bundle to R such that its restriction to each tangent space is actually strongly convex Minkowski norm. So for me, a Finsler metric on a smooth manifold is actually a function from tangent bundle to R such that at non-zero part of the tangent bundle it is smooth, and its restriction to each tangent space is actually strongly convex Minkowski norm. This function f is called Lagrangian of the Finsler structure. And this Finsler structure is called, so in general it is not reversible. So the length of this vector minus chi, it should be at one place it is plus chi. So the length of this minus chi in general is not equal to the length of the vector chi. And if f of minus chi is equal to f of chi for every chi and at every point, this Finsler structure is said to be reversible. Now, here are some examples. So, suppose F0 be a Minkowski norm on Rn, and you just, define at every point, you just translate this Minkowski norm, you just define by this translation. So, this function f from the tangent bundle of Rn to R is defined like this F0 of chi. You don't care about the point x. So, everywhere you have just like Euclidean metric. So, you have the same Minkowski norm at every tangent space. So, such structures, in fact, considered to be the flat space in Minkowski geometry. Now, a Riemannian metric on a manifold again defined a Finsler structure. So, you have this G as a Riemannian metric. So, f of x chi is actually equal to square root of this gx of chi chi. So this actually defined a norm of the vector chi, and this I'm talking about the Finsler structure induced from the Riemannian metric G. Here is another example of a Finsler metric, what is called the famous example Rander's metric. So if G be a Riemannian metric on the manifold M, and theta is a one form, and the condition is required that this one form, the length of this one form with respect to this Riemannian matrix should be less than 1. I mean, a simplest example just I said in for the Minkowski metric actually, right? We have just considered this Euclidean metric. A slight deformation of the Euclidean metric was their Anders metric, and that was an example of the Minkowski metric. So here on a manifold, if you have a Riemannian metric and a one form, you can define a Finsler metric in this way, that the Riemannian norm and deformed by this value of this one form on the vector chi. So this is, I mean, it can be proved that it's actually it satisfies all the condition of a Finsler metric, and this is called Renders metric. You see here, indicatrix is, I mean, the unit sphere in the Euclidean plane is well known. I mean, you translate, and in every tangent space you get Euclidean unit spheres. These are the indicatrices in Riemannian plane, right? So these are, I mean, symmetric ball, and at every point in every tangent space you have these symmetric ball, and these are the indicatrices in the Finsler plane. So at every point these are indicatrices. These are just strongly convex ball. Strongly convex. I mean, the interior is ball and the boundary is indicatrices. Now, the advantage to define this Finsler metric is that we actually wanted, as I said in the first slide, we actually wanted to compute the length of this curve, and now you can define the length of a curve. So the length of a curve gamma defined on some interval I is given by this formula. So you just, I mean, measure the speed of the, which is the, I mean, norm of the velocity vector, and you just integrate to get the length of this curve. And when you can measure this piecewise smooth curves, their length, you can define the distance function. So the distance is the infimum of length of piecewise smooth curves joining the 2 points. Now, interestingly, because of this non-reversibility condition, because this norm of minus j was not equal to norm of j, and therefore the distance here is not symmetric, right? And in fact, the length of any curve is not equal to length of its reversed curve, right? So if gamma is a reverse curve, its length may not be equal to the length of gamma, right? And therefore, its distance satisfy all the condition except this symmetric condition, right? So as we saw that a Riemannian metric is actually an example of a Finsler metric. Any Riemannian metric induces a Finsler structure. So the Hessian of the square of this f square, I mean, why we consider this a strongly convex Finsler metric, although you already have a Minkowski structure. So the reason is that we actually wanted, in some sense, an inner product induced from this Minkowski metric, and this Hessian of f square actually give, in some sense, a kind of inner product on the manifold. So the Hessian of f square induces a direction dependent inner product. So here you see, in Riemannian case, in every tangent space you have a unique inner product, but here in one tangent space this inner product is direction dependent. It's direction dependent, although you see, um, because of this homogeneity condition of this norm, it's direction dependent. I mean, this inner product at the point xj is same as the inner product at the point x2j or x3j and so on. So it's just direction dependent. You take you fix a direction, you get unique inner product in that particular direction. You change the direction, this inner product will change. So whenever we discuss about the inner product in Finsler geometry, we discuss with respect to some direction. So with respect to direction j, the inner product of v and w is given by this formula. If v and w are two vectors with components, say this VI with respect to some coordinate system, then their inner product is given by this formula. And the Finsler metric and this G, this inner product actually is well known by fundamental tensor. So the Finsler metric F and the fundamental tensor G are related by this formula. Here is a very interesting quantity what was introduced by Kartha. So it's well known by Kartha tensor. So it's actually the third derivative. I mean, third derivative of this square of this square of this Minkowski norm. So suppose its component are this, say, given by C, I, J, K. They are actually when you write in terms of the fundamental tensor, it's actually the vertical derivative of this metric tensor, and you can see that it is equal to 0 if this Gij is independent of this direction. And when this metric tensor is independent of the direction, your metric is actually Riemannian. So this Kartha tensor is important in the sense that if it vanishes everywhere, if it vanishes in every direction, then your Finsler metric is actually Riemannian. So the vanishing of Kartha tensor implies your Finsler metric is Riemannian. Yeah. Now let us come to the next stage, that you can measure now the length of curves, and now here is the energy functional. So for any curve gamma, you can define its energy functional as the integral of square of this norm. And the geodesics are actually the critical curves of this energy functional. You can also prove that the critical curves of length functional with constant speed curve is equivalent to the criticalness of this energy functional. So I mean, if a curve gamma is a critical curve for this energy functional, is same as it is a critical curve for the length functional, and it should have constant speed. So the geodesics are defined as the critical curve for energy functional. So it means that it's also critical curve for length functional, that is, you can talk about the minimizing length, and it should have constant speed. Now in local computation, the geodesics are given by a system of second order differential equation, exactly same as you know in Riemannian geometry. The only thing is that here this gamma ijk, what are called Christoffel symbols, they are only function on the manifold, but here these quantities are functions on the tangent bundle, and therefore you have a highly non-linear second order differential equations. But still, because of sufficient smoothness, you can talk about their solution. So if you have a point, initial point and initial direction, at least for start time, you can have a solution of this differential equation. And therefore you can talk about the exponential map. So for a vector u, given initial vector u in a tangent space, let this gamma ut be a geodesic with initial value, initial point and initial velocity, then this exponential map is defined by exactly, it has same definition as you know in Riemannian setup. And you know in Riemannian setup this exponential map is C infinity, but in this Finsler setup, because of you know this the result we proved for this Minkowski norm, somehow it is used here to prove this exponential map is only C1 at origin, and it is C infinity away from the origin. So exponential map in Finsler geometry is only C1 at origin, whereas it is C infinity away from the origin. And interestingly, it is C2 at origin. It's a result by Akbarzadeh that if it is C2 at origin, if and only if it is C infinity at origin. And in that particular case, this Finsler metric is a special name, what is called the Burward metric. So I'm not going in detail about this Barber metric, but I just wanted to emphasize that if you just increase the smoothness of this exponential map by from C1 to C2, it must be C infinity. Now here is, I mean, this oscillating Riemannian metric. So it's a Riemannian metric associated with a Finsler metric, and it's very much important for computation of curvature actually, right? So suppose MF be a smooth manifold with a strongly convex Finsler metric, and x0 xi0 be a point in this non-zero part of the tangent bundle, that is this vector is non-zero. Now a vector field V defined in some neighborhood of the point x0. So this vector field is said to be geodesic extension of xi0 if the integral curves are geodesics of the Finsler metric F, right? In particular, this V, it should not be zero in the whole neighborhood, right? So you are considering a geodesic extension of a vector, but it should not be zero in the whole neighborhood. If such an extension if you have, then I am defining this oscillating Riemannian metric of a Finsler metric F in the direction of this vector field V, and it is defined like this. So what it means, that at every point you are fixing a direction. So if you are fixing a direction, you have a one inner product. That this inner product coming from the Finsler metric is direction dependent. So if at any point you fix the direction, you get exactly unique inner product in that tangent space. So if you have a vector field in some neighborhood, so you just consider that vector field as representative there, and therefore in that tangent space you have exactly one inner product, right? And that is called oscillating Riemann. So in that sense, in that way, in the whole open set, you constructed, I mean, a family of inner product, and that is just parameterized by the point, and therefore is a Riemannian metric. And now you have a Riemannian matrix, so therefore now you can talk about all the geometry what you know about Riemannian geometry. In particular, you can talk about the Riemann curvature, Riemann curvature tensor, right? So Riemann curvature here, I mean, everybody knows. So uh, I mean, you have a kind of Christoffel symbol as we define um, while I was defining this geodesics. So you know this Gi is a quantity. These are called spray coefficient for in Finsler geometry. And in terms of these spray coefficient, you have this formula for Riemann curvature, and that are exactly the Riemann curvature of the this Riemannian metric defined in the previous slide. So in some sense, we have a notion of Riemann curvature in Finsler geometry. And this Riemann curvature, the notion of Riemann curvature induces the notion of flag curvature, which is analog of the sectional curvature in Riemannian geometry. The only thing is that here, I mean, in sectional curvature, in every tangent space, you fix a two-dimensional subspace, and corresponding to that two-dimensional subspace, you have a notion of sectional curvature. But here, in that two-dimensional subspace, again, I'm fixing a pole, right? I'm fixing a pole xi. So with respect to that flag pole, I'm defining this flag curvature as I mean, it has the same formula. The only thing is that everywhere, uh, almost all the things are direction dependent. So that direction, if you fix a direction, it is it is uh, it is called the flag curvature at a point x in direction of xi. So if you fix a flagpole xi, and in a two-dimensional subspace P in tangent space TXM, and suppose I'm taking this V as a vector transverse edge, that is this xi and V, they span this subspace P, then the flag curvature is given by this formula. It's exactly had the same formula as you know in Riemannian geometry. So here it depends on the point, it depends on the flagpole, it depends on the two-dimensional subspace P. But it will not depend on this transverse. You can take any transverse A's, and it can be proved that it is independent of this transverse edge V. So it depends on the point, it depends on the flagpole, and it depends on the cloth part of the flag, that is the two-dimensional subspace. And that is why it is called flag curvature. Okay, so that I already said. So in Finsler geometry, a Finsler metric is said to be constant flag curvature if it is independent of this chi, independent of x, and independent of p, right? So for every x, for every chi, and for every p, if this flag curvature is constant, we say that it is a constant flag curvature. It's said to be scalar flag curvature if it is independent of this two-dimensional subspace, that only depend on x and this flagpole. So if cloth part disappear in the formula, we say that it is a scalar flag curvature. And as everybody knows that in a Riemannian metric of constant sectional curvature is completely classified. The classification is known that locally it's Euclidean or spherical or hyperbolic metric, but in Finsler geometry it's an open problem. This Rander's metric, what I defined in the previous slides, only this case of Rander's metric of constant flag curvature was completely classified, and I mean, but for different metrics people classified and is going on, but in general it is not done yet. Okay, now let us come to another interesting example, what is called Funk metric in a convex domain in Rn. So let us consider a convex set omega in Rn, and what is called this tautological Funk-Finsler structure, right? So this omega um, is a convex set. So at each point, at each point of omega, you can think of this omega itself as a unit ball in the tangent space of that particular point, right? So for example, if this is my convex set and you take uh, so this is suppose this is a convex set, for the moment you can assume as a unit ball, right? And it may not be this as it's look like, so maybe I can draw some picture here. So maybe you can think of, suppose this is my convex set, and take a point here, and I'm declaring that this is unit ball, this is my unit ball in the tangent space of the point this, right? You take another point, right? This point, for this point you identify your tangent space with your space Rn, and in that tangent space you can think of the same set as unit ball centered at this particular point. So for various point, this ball is fixed, and you can think of that ball as unit ball in that particular tangent space of that particular point, right? So so in this way you can have a notion of norm in every tangent space, right? If you know this unit ball in a tangent space, you can talk about the norm. For example, so if this is, suppose this is my unit vector, and you want to measure the length of this vector, right? So if suppose this is 2 times, you can say yes, this is the, I mean, the length of this vector is 2. So the length of any vector, if you want to measure the length of a vector this, you just see that how much it may be k times. If this unit vector is this vector, then its length is k. You can use this the positive homogeneity, right? But the length of this vector is 1 here, it may not be equal to the length of this vector. The length of this vector is, say, here 1, the length of this vector is also 1. So it may not be symmetric, right? So if you know the unit ball in every tangent space, you can have a Finsler structure on that particular manifold. So here, this is special Finsler structure is called tautological Funk-Finsler structure, right? So suppose at a point x you want to measure the norm of this vector chi. What you have to do, you just see that x plus, suppose 1 upon t times xi. I mean, suppose it's 2 times xi is intersecting this boundary, that is 2 times xi is this unit vector. It means this norm of xi should be 1 upon 2, right? So that is given here. So in infimum of this t, when it's going to intersect this point A, and you have to take the infimum of that real number t. So for instance, if 2 times xi is at the boundary, it meets at the boundary, then the norm of xi is equal to 1 upon 2. So I mean something like that. So you can have this Finsler structure, and this is called Funk-Finsler structure for this convex set omega. In particular, if this convex set omega is Euclidean unit ball, if this omega is Euclidean unit ball, this x plus xi over this fx xi, which was the norm of this xi, it will be a point on the boundary. So its the square norm is equal to 1, and a simple computation gives this quadratic equation. And if you just solve, I mean, you can see this is the angular bracket as the inner product, Euclidean inner product, and this is the Euclidean norm of xi, Euclidean norm of x. So a simple computation gives this formula. So the Finsler structure for this, this unit ball is, Funk-Finsler structure for this unit ball is given by this formula, right? You can see here this first expression. Those who know the various models of hyperbolic geometry, they must know that this is actually the Klein metric in open unit disk. This is Klein metric, standard Klein metric in open unit disk, and this is a one form in open unit disk, right? So this Finsler structure is actually the sum of a kind of Riemannian metric and a one form and a one form, and in fact this one form is a very special one form, is closed one form, and this is the standard Klein metric, right? And by some simple computation, you can observe that this Funk-Finsler structure is actually a Randers metric given by this previous equation. It is called Randers metric because the sum of a Riemannian metric is a kind of deformation of a Riemannian metric by some one form. And the geodesics of this Funk-Finsler structure on the unit disk, they are line segments. So this is an interesting remark that in this case, the geodesics are the shortest um, paths are actually the line segment in open unit disk. And further, the distance induced by this Finsler structure is actually given by this formula. So here, so suppose this is my unit disk and you have 2 points x1 and x2, and you take this ray, suppose this is my x1, this is my x2, and it intersect this boundary at a point A. So now you compute the distance from x. This is the Euclidean distance from x1 to A, Euclidean distance from x2 to A, and take its log. So for instance, you can see that when this x2 going closer and closer to this boundary point, this distance becomes closer to 0, and this becomes infinity. So as this x2 going closer and closer to A, the distance from x1 to x2 going to infinity. So it's a kind of you see here it's a forward complete. It's a forward complete Finsler metric, but the distance from x1 to x2 is not equal to distance from x2 to x1, because when you compute the distance from x2 to x1, you have to take this ray from x2 to x1, and it will intersect somewhere at the point B, and then you have to take the ratio of this x2 to b and x1 to b, right? So in that sense, it's obvious that the distance from x1 to x2 is not equal to distance from x2 to x1. And further, as I already uh, talked about the flag curvature, it can be shown that this Finsler structure has constant flag curvature minus 1 upon 4. It has constant flag curvature minus 1 upon 4. And it's a forward complete, but not backward complete. It's not backward complete. The next example of Finsler metric is the Hilbert metric. Now, the Hilbert-Finsler structure in a convex domain omega is actually the arithmetic symmetrization of the tautological Funk-Finsler structure. So, if fx xi be the Funk-Finsler structure for a domain omega, then you consider this reverse Funk structure and you take its arithmetic symmetrization, right? So, this Hilbert-Finsler structure is the arithmetic symmetrization of Funk-Finsler structure. And here you can see the symmetry comes, right? So if you take x1, x2, and suppose this ray from x1 to x2 hits this boundary at the point A, and this ray from x2 to x1, it hits this boundary at the point B, this both point A and B will appear in the formula of the distance. So here is the proposition with respect to this Hilbert-Finsler structure. So the Hilbert-Finsler structure is exactly given by the formula of the Klein metric. So for unit ball, if your omega is the unit ball, if your convex domain is unit ball, for unit ball, the Hilbert-Finsler structure has exactly the same formula as your Klein metric of hyperbolic geometry. Here again, the geodesics of this Hilbert structure on open unit disk are line segments in open unit disk. The distance formula is just, the arithmetic symmetrization of what we got in the Funk formula, that is x1 minus a upon x2 minus a and plus log of x2 minus b upon x1 minus b. You can also see that this x1, x2, a and b, this is actually cross ratio of these 4 points lie on a line, right? So this Hilbert distance has this interesting formula. And this Hilbert-Finsler structure on open unit disk is also of constant flag curvature, but it's of constant flag curvature minus 1 because it's a form of Klein metric, and Klein metric has a constant flag curvature minus 1. And this Hilbert metric is both forward as well as backward complete. Okay, now here is the interesting characterization for this Hilbert metric. So the Hilbert metric F in a bounded domain omega with a smooth, strongly convex boundary, it is Riemannian if and only if this omega is an ellipsoid. So if it is an ellipsoid, so for instance, we just computed for this omega in the unit Euclidean ball, right? And you saw that it's a Klein metric, which is a Riemannian metric. So for ellipsoid, this Finsler metric is Riemannian. It's actually if and only if condition. So if it's not ellipsoid, it cannot be Riemannian. And this is an interesting characterization. If F is a strongly convex Finsler metric on a bounded convex domain omega, then F is Hilbert metric of that domain. This Finsler structure is actually Hilbert metric if and only if this projectively flat means this the geodesics are line segment. So this projectively flat has a meaning that the geodesics are line segment. So if and only if the geodesics are line segment, it's complete and has constant -1 constant negative flag curvature, right? So this is an interesting uh, uh, characterization of this Funk pervert metric. So I will give the proper reference for this. In fact, it's appeared in a book by Professor Papadopoulos and Triano. So I will show in the references. So all these theorems are proved there. Those who are interested can go through it. Now further, you can see this Funk metric in various perspective also, right? So for instance, everybody know, like in hyperbolic geometry. So you know this Lorentzian metric is a non-positive definite uh, metric in R3. In fact, you can think of in Rn plus 1 also. So it's Lorentzian metric. It has signature, I mean, minus 1, 1, 1, 1 n times. So it's a non-positive definite Riemannian metric. But when you pull back this Lorentzian metric on hyperboloid of upper sheet of hyperboloid of 2 sheet is actually a positive definite Riemannian metric, and what is called hyperbolic metric on the unit disk. And it depends on what immersion you are considering. You can get Klein metric or Poincare metric on the open unit disk. So in a similar way, you can also construct a non-positive definite Randers metric on upper half space whose pullback on hyperboloid of 2 sheet is exactly the Funk metric in unit disk. And that is, it was, I mean, recently point out, and the paper, I mean, appeared last year. So this was the uh, Lorentzian metric in R3, and it was defined by this one form. So to get a non-positive definite Randers metric, and its pullback on the upper half of the hyperboloid of 2 sheet is actually the Funk metric. And this is another, interesting realization for this Funk metric as a solution of Zermelo navigation problem. So Zermelo actually posed and answered the following question: that uh, if you consider in calm water, right? So suppose some ship is sailing in this calm water from one point, or from this point, and if there is no flow in the water, in unit time it reaches, I mean, same distance, same Euclidean distance, right? But suppose there is a flow of water, and in unit time, this you have to sail the ship. It will take some, I mean, the path like this in unit time. I mean, in direction of the water it may go some longer distance, and against the water, I mean, in smaller distance, something like this, right? So this is my unit ball for this I mean, for this boat, right? Now, in fact, you can you can prove that the shortest path here with this flow, it's not actually the geodesic of a Riemannian metric. It turns out that it's a geodesic of a Finsler metric, in fact Randers metric. So if this convex set, so you can take any, in fact, convex set omega which contains the origin, then the Funk Finsler structure gives the solution of Zermelo navigation problem for this special uh, flow of the vector field given by this zx is equal to x, right? For this special vector field, its solution of the Zermelo navigation problem. So this Funk metric is also interesting from this viewpoint. Now, you see this Funk metric, which was we define uh, that the distance between 2 points in a convex set was this log of x1 minus, so it was defined like this. So for any convex set, this x1 x2, suppose this ray intersect this boundary at a point A, x1 and x2. So it was defined like this: the x1 minus a, the Euclidean distance from x1 to a, and Euclidean distance from x2 to a. You take the ratio, take the log, that is the Funk distance between 2 points. Now in 2013, Sir Papadopoulos and Yamada, they define the variational Funke distance. And how it defined? So you take this, this hyperplane, right? This take hyperplane, and suppose this hyperplane intersect at a point T. So you compute the distance from this x2, the perpendicular distance from x2 to this hyperplane, and the perpendicular distance from x1 to hyperplane, right? And by similarity you can prove that the supremum of this exists when this is strictly convex. It exists at when this hyperplane is tangent at the point A, and there the ratio of x2 to A and x1 to A is same as the ratio of these these two distances. I mean the distance from x2 and x1 to this hyperplane, right? So but through this approach, I mean several difficult problem, I mean, can be solved very easily. For instance, the if you want to prove the triangle inequality through this approach, it can be proved very easily. So somehow this ratio of distances, they are important, and it was considered to define this variational Funke distance. Now they actually they also generalize it to the spaces of constant curvature. So here, in Euclidean geometry, this you consider the two triangles, the two similar triangles, say this A B C and A B dash C dash, and here this sign of A you can write as ratio of BC is to AC, or B dash C dash to A dash C dash. But in spherical geometry, when you consider the uh, the ratio of length of these sides, you have to consider here the weight function, right? So it's not BC upon AC. In fact, it's sine of BC is to sine of AC. In spherical geometry, only simply the ratio of the length of the sides will not appear, but it will be this weighted by this sine function. That is, sine of A is actually equal to sine BC upon sine AC, or sine B dash C dash sine A dash C, AC dash. And similarly, in hyperbolic geometry, this will appear as uh, weighted by this hyperbolic functions. And then they define this distance between 2 point x1 x2, what is called the Funke metric in the negative curvature spaces, as the log of sine hyperbolic distance from x1 to A, hyperbolic distance from x2 to A, take their sine hyperbolic, take the logarithm, and that is the distance between 2 point in the uh, negative curvature in a convex set in negative curvature spaces. And they also computed this Finsler structure there. In a similar way, they computed for this positively curved spaces. So suppose x1 and x2 be 2 points in a convex set omega on this sphere. Suppose this omega is a convex set on the sphere, and suppose this geodesic, this great circle x1 passing through x1 and x2 intersect the boundary at A. So you compute the spherical distance from x1 to A, x2 to A, take their sign and take the ratio, and that is the Funke formula for a convex set on the sphere. And again, they computed the Finsler structure for this Funke metric given by this, and the local, in fact, infinitesimal structure of this Funke formula in local coordinate system. It was recently we have computed, in fact, and uh, in fact we got a formula for um, all the three spaces, for Euclidean space, for hyperbolic space, for spherical space, in a single formula. It's given by this. So I think my time is over also, and it's best time to stop. So those who are interested to go through, it was just an overview of the Finsler geometry, some aspect of Finsler geometry, you can say, and most of the results are already proved in. I mean, those who are interested can go through this interesting book of Papadopoulos and Traiano, and this paper also, weak Finsler structure and Unk weak metric. So thank you very much for your patience, and I'm happy if you have any query or question.
Yeah. Hello, can you hear?
Yes, yes, yes.
Yeah. So, are there any questions? No. Thank you very much.
Okay, okay.
And
Thank you, thank you, thank you.
it would have been nice if you could have
Yeah,
you
yeah,
would have been
definitely.
able to come. So,
Yeah, yeah. So in fact, the train through which I was about to come, it is still not reached the New Delhi railway station. It's too
yeah, I
late,
know.
too late, too late. Yeah, yeah,
We'll probably reach the Bahakum.
yeah, yeah, yeah. Yeah, yeah. Okay, so thank you, thank you, thank you.
Okay.